Okay, this is just a short video to explain why we don't run generators that would power our home or power a building with a small electric motor. And basically, there are three reasons, so I'm going to put them up here. I'm going to put a number one up here, and then I'm going to make sure I can see it on the camera. Woo, barely. Okay, but number one is magnetic drag. Number two is Lenz's law. And number three is heat. So let's take these three items in order and talk about them and how we could possibly overcome them if we have a brain in our head. Okay, the first thing is magnetic drag, and that's this idea is that when you have a rotor here and you have magnets on the rotor, and the rotor's going around and around and around in a circle, and you place a coil in front of this rotor with an iron core in it. As each one of these magnets go by, it's attracted to the iron in the core of that coil, and it slows down a little bit because as it lines right up and it tries to pull away, it actually accelerates as it's coming in because it wants to get there, but then as it's trying to leave, all the gains that you make as it's trying to leave are eliminated, and there's a brief period of time when the two are perfectly aligned with each other, where it's neither coming in nor going away, but is directly lined up to it, where there's a magnetic lock that occurs, and this is a plus, this is a minus, they cancel each other out, but that moment of magnetic lock causes drag. At slow speeds, it causes cogging, where the coil goes room, 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 around in a circle as the magnets are going by the coil. At high speed, that cogging appears to go away, but there is always going to be magnetic drag. And so if I have a coil here on this side of the rotor, and another one on the back side, and one here, and another one on the back side, and another one here, and one on the back side, and one here, and one on the back side, and one here, and one on the back side, and one here, and one on the back side, and one here, and one on the back side, that magnetic drag is so tremendous that the motor that's trying to turn this rotor will burn up. In fact, it'll burn up with only about 4 coils, 2 on the front and 2 on the back. It'll overload most small motors. Now you can get some really big motors that got tons of torque and pull lots of amps, but a small motor that's only rated for 25 or 30 amps, it's gonna burn up when you're trying to do this. So how can you get rid of that magnetic lock? Well, gosh, let's apply some rocket science here and see if we can figure out a way. So here's our rotor again, and I'm just going to put 4 magnets on this rotor, so you can see as long as it's an even number of magnets, it doesn't matter. But you have to have an even number of magnets on the rotor. And what you do is this: you put your coils here, and of course there's also one on the back. So you've got 2 coils that are attracted to this magnet that's on the rotor. It's right between them, so it's attracted to them. But down here, because if it's an even number of magnets on the rotor, directly across from it, you put magnets in your stator that line up with this magnet in repulsion. So one on each side that line up with your stator in repulsion. And if they're adjustable, so they can go in and out, you can balance the magnetic attraction that's occurring here with repulsion here. Because when you put a north magnet, you put a magnet on the rotor, it'll have north on one side and it'll have south on the other. So you put a north magnet here and a south magnet here, and now they're repelling the magnet on the rotor. And if you adjust them, you can get a perfect balance between this attraction and this repulsion. And so then you have 2 coils here, one on the front and one on the back, and you have magnets in repulsion there. And if you have, I'm running out of, shouldn't have left the cap off my pen. And if you have another rotor here with a coil around it. I mean, another magnet here with a coil around it. You have another magnet over here that is under magnetic repulsion. And if you have one here with a coil around it, you have one here that's in magnetic repulsion. And all you have to have is make sure you have an even number of magnets on the rotor and an odd number of coils. And so with 6 magnets on the rotor and 5 coils, 1, 2, 3, 4, 5, you can see that with the round circle here, where the magnets are coming around, anytime the magnet on the rotor here is lined up with the coil, like this, if you go directly across, there's an empty space between the coils where you can put a magnet in repulsion. The same thing here. Directly across, directly across, directly across. There's always an empty space where you can put a magnet in repulsion. And that's the way my generator is built. If I were to show it to you, and I can run and grab it really quick, I think. Oops. Let's see here. You can see here are the holes for the coils. There's 1, 2, 3, 4, 5 holes for the coils. And see these tiny holes right here? If you flip it over on the back side, you will see that the center of the coil is right here, and this is a hole for the cord to stick through. And here's the magnet and repulsion. So here's a coil, magnet and repulsion. 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 Just like I said. And that's the way this generator is set up to operate. And I'm going to go through this more in depth in a different video, but I wanted to show it to you. So, the first problem that we have to deal with, which is magnetic drag, we don't have to deal with that anymore. It's gone. We just eliminated magnetic drag. Okay, now let's talk about Lenz's law. Oops. All right, Lenz's law says that when you have your coil here with its iron core, man, I really ruined that pen. I'm gonna have to let it set. When you have your coil with an iron core and you have a rotor with a magnet coming around, that the magnet on the rotor, and this is a big rotor here, and it's got magnets all around it, and they're going to go by this coil. As this magnet is coming around, it induces, and if this coil is connected to a load, like a light bulb out here, there's our light bulb, ding, okay. If the coil is connected to a load, and this magnet comes around, it induces a magnetic field in this coil, in this core. Actually, what it does is it creates magnetism in the core. The magnetism in the core creates electricity in the coil. The coil then turns the center core material, which is iron, into an electromagnet with an electromagnetic field that pushes away the approaching magnet. And so, as each magnet tries to come around to the coil, it doesn't want to do it, okay, because there's a magnetic field here that's pushing the approaching magnet away. That's Lenz's law. And when you have a lot of magnets on the coil, every single one of them reacts badly to approaching that core. Now, there's a patent by Nikola Tesla that says if you wind coils in a specific manner, it increases the capacitance of the coil. And the coils that I wind for my generator are 24 strands of number 23 magnet wire, and you take 8 strands and connect them in series, and then 8 more strands in series, and then 8 more strands in series, and you end up with 3 wires coming off the coil but each one of those 3 wires is composed of 8 wires, where the end of one wire is connected to the beginning of the next wire. So all the wires are wrapped in parallel on the coil, but then they're connected in series. If that's too difficult to understand, I can explain it further some other time. But anyway, so what Tesla said is when you increase the capacitance in the coil, well, all of a sudden it takes longer for the reaction to happen. And if you look at the timeline, here's what happens. Okay, the magnet comes into contact with the magnetic field and begins to create flux in the core of the coil, and it has to create so much flux before the coil begins to create electricity. And as soon as the coil begins to create electricity, it starts to turn this into an electromagnet. And now the electromagnet is repelling the approaching magnet. So you have a timeline of events that happen. Well, if you increase the capacitance of the coil, it takes longer for you to go from A to B here in the timeline, but the magnet, by the time this happens, is already here. And it's lined up over the top of the coil, where all of a sudden the coil creates an electromagnet that is in repulsion to the approaching magnet, only the approaching magnet is already there, and so it shoots it on by and actually causes a speed up of the rotor. It takes a coil that's wound a specific way, as I just described. It takes a certain RPM of the rotor, but every coil will speed up under load at the right RPM, because if you're turning the rotor fast enough, obviously this magnet's going to get there as fast as you want it to. But because we're turning our rotor slower, we wind our coils with a higher capacitance, so that when this magnet starts to affect the core of the coil, it's already lined up before that can take place, and it pushes it on by. So we just eliminated Lenz's law. Okay. The third thing under consideration is heat. Now, because heat is such an issue, most modern generators don't use iron cores in their coils. They use ferrite or met glass or some composite material that doesn't radiate heat as badly as iron does. But one of the disadvantages of those materials is they absorb flux a lot quicker, creating this magnetic repulsion effect a lot quicker. And so you really got to have incredible RPMs with those kinds of materials to get this same reaction. In most modern generators, there's no way that they will be able to take advantage of this. But because we're building an old-time generator here with an iron core, we can take advantage of all of this. But now we do have to deal with the issue of heat. So how do you deal with the issue of heat? Well, I'm going to draw kind of a side view of this. Here's your rotor going by, your big tall rotor, and here's the magnet on the rotor, and here's your iron core sticking out of your coil a little bit, and there's your coil. And what you do is you let the core of the coil, the iron core, stick out the back a little bit, and you take a piece of PVC pipe and you put a cap on it, and you drill a 3/4 inch hole in it, and you slide it over here, and you epoxy it in place, and you fill the pipe up with water. And you can do this to all your coils, and you can interconnect them, and you can have water circulating back there, and that water just keeps the core cool. So you heat water, you cool your core at the same time. And if you really want to get environmentally safe so that this water can be reused, what you do is you have a tube with water in it that has a fill spout on it, but around that you have another sealed tube with circulating water in it, so it circulates around in here around the outside of the tube that has permanent water in it, and you never, this doesn't become drinking water or anything that you use, but the water that's circulating around the outside, because it's shielded from the iron in the core by this other tube. You can use it for drinking water, you can use it for anything you want. It's perfectly good water because you're using, you know, the grades of materials that allow you to drink the water that was inside this plastic, because it never touches the iron in the core. So that eliminates the heat. You've taken the three things that make it impossible to run an electric motor or run a generator with a small electric motor, and you've gotten rid of them. So that my little MY1020 Razor scooter motor that runs on maximum of 36 amps only needs about 10 to 12 amps to run my generator, and my generator has 12 coils, each putting out 130 volts at 1.5 amps, and that's just a little over 2,000 watts that the generator puts out, and that tells you what it runs on. It runs on less than 300, and it puts out almost, well, a little over 2,000. So that is the situation, and that's what we can do.